Hello everyone, let's talk about transformations. A transformation is a modification done to a figure such that it changes the shape and or size of the figure. If we want to transform something, say we had triangle ABC, and we just want to move it over. This original triangle is called our pre-image, or you can just refer to it as the original. The new triangle is called the image. And we denote the difference between a pre-image and an image and their relationship together by using the same letters for the points, so A, B, C, except we use tick marks as a superscript of them. So it would be triangle ABC is transformed to triangle A prime, B prime, and C prime. So that's our notation for that. If you had a point and it just kept transforming over and over again, you would increase the number of tick marks in your superscript. So if you had point A and you moved it over here, that will be A prime. And then if you took A prime and you moved it down here, that will be A double prime. And if you took A double prime and you moved it over here, that will be A triple prime. So that's our pre-image, that's our first image, our second image, and our third image. That's how you differentiate between them. So if you take Optimus and you transform it, it becomes Optimus Prime. Make sense? All right. So in general, there's two types of transformations. There's isometric and non-isometric. I'm going to give you the definition of an isometric transformation, and I hope you can extrapolate the definition of a non-isometric transformation from that. So an isometric transformation is any transformation that does not change the shape or the size of the image. Some examples of isometric transformations are translations, which you may be more familiar with as just calling them shifts. But that's just taking an object and moving it left, right, up, down, or any combination of those. Another isometric transformation is a reflection. Even though it changes the orientation of the object, a reflection reflecting it over a line does not change the shape nor the size. If it's a triangle, you're still going to have a triangle, and it's going to be a congruent triangle to the original triangle, just oriented differently. And another type of isometry is a rotation. If you take an object and you rotate it, look, those words, still the same words, but they're just oriented differently, but nothing's changed about them. They've just been rotated. So they're still the same words, but they're rotated, nothing's changed. So those are isometries. And then for a non-isometric transformation, it's a dilation. You may be more familiar with the term stretch or shrink. Stretches and shrinks are both dilations. They're just, one's a compression and one's an expansion. So these are isometries and non-isometries. Let's go through the isometries first. Our first isometry was a translation. So that's shifting something left, right, up, down, or some combination of them. So let's say we had the point XY and we wanted to translate up 5 and left 2. This point If you were to take it up 5, up and down modifies the y-coordinate, and going up is adding. Left and right modifies the x-coordinate, and going left is subtracting. So this would be the image of that pre-image with this transformation. There is shorthand you can use for these transformations, not just translations. But for translation, it starts with the letter T, so we use a T. And the subscript of this T tells us what we're doing. On the first coordinate, we're subtracting 2. On the second coordinate, we're adding 5. So it's a -2 horizontally, it's a +5 vertically of our point xy. So that's our transformation. So if we had the notation t 3 negative 9 of 1411, this is telling us to take the point 1411, translate it right 3 and down 9. So right 3 from 14 is adding 3 to 14, so 17, and down 9 from 11 is 2. So this is your result. That's your image after doing that translation. So that's translations. Next up we had reflections. So reflection, we're reflecting over a line. Now some of them are easier than others because some of the lines are very straightforward. Now, the notation for reflection, it's a lowercase r. And the subscript is what you're reflecting over. So let's say we want to reflect over the x-axis. If we had xy, if we want to take the point xy and reflect it over the x-axis, that's the horizontal line. So you're either going from above to below or below to above. You're not moving laterally, so the x doesn't change, but the y is opposite. It will be the opposite for reflecting over the y-axis. It will be the reflecting over the vertical, so you're going from the right to the left or the left to the right. So horizontally is what it's the opposite, and vertically there's no change. A couple other easy lines to reflect over are y equals x and y equals negative x. Now for y equals x, that's the line with the slope of 1. So if we are below in, say, quadrant 1, the reflection is going to still be in quadrant 1. So it's still going to be positive, positive. If we're below in quadrant 4, it's going to be above in quadrant 2. So it's going to go from positive, negative to negative, positive. And if we're below in quadrant 3, it's going to reflect to above in quadrant 3. So it's going to go from negative, negative to negative, negative. So whatever the sign of your first coordinate was becomes the sign of your second coordinate. Whatever the sign of your second coordinate was becomes the sign of your first coordinate. Really all you're doing is switching your x and y. And for y over y equals negative x, you're switching your x and y and the sign. All right, so these are some basic reflections, reflecting over the x-axis, over the y-axis, or y equals x and y equals negative x. But those aren't the only lines in the coordinate plane. There are plenty of lines in the coordinate plane. But we know how to find out the reflection algebraically because we learned a lot about lines. Let's say this line was y equals 2x minus 4. If you have a point on one side, I'm just going to call it A, its reflection, A prime, would be about here. What's happening with these is that the distance from A to the line of reflection and the distance from A prime to the line of reflection is the same, and distance from a point to a line is perpendicular. So you, if you had this point, would be able to reflect over this line because this line of reflection is the perpendicular bisector of the segment containing the point and its image. So you could find out the equation of this line, find out where these two lines intersect, the line containing the point and its image and our line of reflection. That is going to be the midpoint of A and A prime. And if you know a point and its midpoint, you can find the other endpoint of the segment. So that's how you can find any reflection in the coordinate plane. Now, rotations, we have the tools to find any rotation, but we're not going to do every rotation. We are just going to stick with multiples of 90 for now. If you wanted to do non-multiples of 90, you would have to use trigonometry. You would establish triangles and work from there. It's a lot easier with the trig you will learn when you take pre-calculus and trig your junior year. So for now, let's just work with the rotations of multiples of 90. So, well, rotation, reflection both start with R. So our shorthand for rotation is going to also be R, but it's a capital R. When we did reflection, it was a lowercase r. Rotation, it's going to be a capital R. And we're going to do multiples of 90 degrees. So 90, 180, 270, and 360. So one of these is really, really easy. One of them is just super mega easy. And that's rotating 360 degrees. Because if you go full circle, you just end up where you started. The rest of them, not so much. Oh, one thing I forgot to mention is if it doesn't tell you your center of rotation, it is implied that the center of rotation is the origin. So if we have our original point, I'm just going to say xy. And xy could be anywhere in the plane. I'm just putting it in the first quadrant just because it's the easiest for us to grasp when it's positive. With this xy, you could make that right triangle. Now, if you want to rotate it, if you want to rotate this about the origin, it's going to be somewhere on the circle with that radius. Because if you're rotating it about the origin, it's going to be equidistant from the origin, regardless where you rotate it to. And imagine that circle's not terrible. So if we want to rotate at 90 degrees, we're actually going to be rotating counterclockwise. So positive angles are counterclockwise. And that's because of how we count our quadrants. It's quadrant 1, quadrant 2, 3, 4. So we are progressing through the quadrants in order. So we start in quadrant 1, so we would go to quadrant 2 next. So that's going counterclockwise. So if we want to rotate this 90 degrees, this radius and that radius will have a 90-degree angle between them. And it's going to end up here. Well, if this angle and this angle are in this right triangle, these two angles are complementary. And if this adds up to is 90 degrees, this angle and that angle will be complementary. So this is the same as that. So this triangle is the same as that triangle with congruent hypotenuses. Those angles are congruent. So we've got two congruent triangles. This was x, this was y. So this is y, this is x. So we're going y in the negative direction and x in the positive direction. So that means when you rotate 90 degrees, it's negative y, comma x. You swap the coordinates and then change the sign of the new x. If you want to rotate 180 degrees, you could say you're doing 290 degrees, or rotating 180 degrees is going half the circle. This is a diameter, so the center 0, 0 is the midpoint of this diameter. If that's xy, that's 0, 0. This would be negative x, negative y. So for 180 degrees, it's negative x, negative y. And then 270 is going 90 and then an additional 180 degrees. So you're doing this transformation and then an additional 180 degrees on that. So you're doing this to that point to get 270, which you're just changing the signs of the coordinates. So it's y, negative x. So these are our rules for rotations of multiples of 90 degrees. And those are all our isometric transformations. Our non-isometric transformations are dilations, you may have heard of them as stretches and shrinks. Stretches are more appropriately called expansions. And a shrink is more appropriately called a psychologist. I'm just kidding, it's a compression. All right. So for our shorthand for translation was a T, for rotation was a capital R, for reflection was a lowercase r. It is a D for dilation. And our dilation, it's what the factor of dilation is. So if we have dilation of 3 of xy, all that's saying to do is multiply by 3 to the x and y coordinates. If we had 2/5 of xy, you multiply by 2/5. Oops, forgot my x. Next year, you'll talk about directional dilations, where you're just doing a horizontal stretch or shrink, or a vertical expansion or compression. But for this year, we're not dealing with that. We're dealing with just a whole dilation. Now, I want to warn you that on MCAS, they use garbage notation. So you may see that. Okay? Realistically, that should be negative 3x, negative 3y. So that should be a reflection and a dilation by a factor of 3. But for some strange reason, and none of the math teachers in our school can figure out why, they have decided to say that a negative subscript means it is a shrink. We don't know why. We can't find other texts that use that. They just have decided that. And this showed up on MCAS a few years ago, and we were a little baffled. But it said a dilation of by a factor of negative 3. So most people answered negative 3x, negative 3y, which is really what it is. But they mean when it's negative, it's a shrink. When it's positive, it's a stretch. So just to let you know, if next year on MCAS you see this, they ask a dilation of a negative value, they're really looking for a compression. It's wrong. It hurts me to show you that, but I need to warn you for the mistakes that are made that you might encounter. All right. But something doesn't just take one transformation. You can do multiple transformations on something, and that's called a composition of transformations. The notation for that is if you had like D2, T5 negative 1, R 180. If we'll say 3, 1. If you have a composition of functions, you work this way. So the first result is going to be doing you first do the rotation 180 degrees. So the first result will be negative 3, negative 1. Then after that, you do what's next. You do the translation. Right 5 and down 1. So right 5 from negative 3 is 2. Down 1 from negative 1 is negative 2. And then lastly, our dilation by a factor of 2. Which would be 4, negative 4. All right, so this would be the result of that composition. All right, I think that's it. Have a great day. Bye.